Hi folks, welcome back to Physics with Captain Rod. I'm making this one here to help you out with numbers 17 and 18 on your Unit 4 homework. So imagine a block of aluminum, 50 by 50 by 50. Might even start with a quick little sketch of that aluminum. I'll just put X, X, and X for now. How much heat is needed to raise the temperature by 30 degrees? So that's just a heat temperature question. That has to do with specific heat. So start by writing out, Q equals mc delta T. Now, the mass of this aluminum is not given. What we have are dimensions, enough to get the volume. So start by calculating the volume of that block, and then look up the density of aluminum. And density, all right, this is some number that has units of kilograms per cubic meter. Density is mass over volume. So look up the density of aluminum in units of kilogram per cubic meter, and then take your volume and you can calculate the mass, right? And that's going to be this value. Then look up the specific heat of aluminum, and the delta T is given in the problem. And that'll get you the heat, how much heat is needed to raise the temperature of that aluminum. All right, now, how much work is done by the expansion of the block against air pressure? Whoops, I guess I got to fix that. I'll do that a little later. All right, so work done by a gas is pressure times change in volume. So although it doesn't state it, I guess, what I had meant is, against air pressure. So what I meant is atmospheric pressure. So go ahead and use roughly 10 to the 5th newtons per square meter. And we're going to need to calculate a change in volume. So hopefully you've watched my videos about expansion of materials, but just a quick little review here. Materials expand linearly with temperature. So your change in length, right, is alpha times your original length times the temperature change. Changes in area, right, there's what's called a coefficient of area expansion. I usually put beta and then times the original area times the temperature change. And then changes in volume, also proportional to the temperature changes. I think usually I use something like gamma for the volume proportionality constants times, your original volume times your temperature change. Now this seems like a lot, but basically these equations are just saying each one of these changes is directly proportional to the temperature changes. And then this one's called the coefficient of linear expansion, coefficient of area expansion, coefficient of volume expansion. Once you know this one, just look up that coefficient of linear expansion for aluminum. And then the beta, the area expansion, is approximately twice alpha. And if you needed a volume one, which we do in this problem, you can go ahead and use 3 times alpha. That's how you get your change in volume for the work term here. That should get you through number 17. All right, number 18, how much energy is needed to raise the temperature of an aluminum pot, 0.8 degree or 0.8 kilograms, which contains 2 kilograms of water at 40 degrees centigrade to the boiling temperature of water. Let's start with a picture as usual. We have our pot here, and it's got some water in it. And we have an initial temperature of our system here, 40 C. Now, let's see. We're looking for the heat needed to raise that system to 100 C. Now, keep in mind how this stuff works here. Right? When we do a temperature against heat added, and I'm going to talk about for the water, we're starting at 40. As we start adding heat, temperature goes up linearly. Now you might wonder, can we just ignore the aluminum? Well, let me just put that on hold for a minute. Let's just talk about just the water for a moment. Right, until we're up to 100 degrees C. Right, and it says to the boiling temperature. So that's about it for this question. So aluminum is a good conductor of heat. So basically, as the water temperatures goes up, the aluminum is going to go up with it. So our heat terms, we're going to have an mc delta T for the water and another one I'll put a larger M and a larger C and a but the same delta T for the aluminum. So you're going to have an MC delta T for the water and an MC delta T for the aluminum. Masses are given, and you'll just have to look up the corresponding specific heats. Let's see, what is the heat transfer rate if the process takes 15 minutes? So just take that heat total and divide by the 15 minutes, right? And you're going to get a number with units of joules per minute, which is perfectly acceptable. It doesn't actually specifically say. Let's see, what is the cost, electrical cost, assuming 100% efficiency and 16 cents per kilowatt hour? So let's talk about this. We can either take this and convert it to joules, or we can take this number and convert it to kilowatt hours. And the way you do the conversion is this. 1 kilowatt hour, you just take it at face value, is 1,000, because kilo means 1,000, watt is a joule per second, and an hour is 3,600 seconds. So 3.6 million. There's 3.6 million joules per kilowatt hour, and then you can calculate a number. So that should get you through that homework problem. Have a great day.